Okay, so today we start exponential functions. We're doing the first couple of sections out of chapter 6, but it won't take that long. I think. I hope. Because we have 15 minutes less than, normal. So the idea today is we intro exponential functions. You can do a little bit of work on that after we're done if you want, or you can work on the rational expressions. Tomorrow will be straight review of rational expressions, so your chance to ask any questions, get everything straightened out. Friday, that is Friday. So Monday will be the test. And it's first thing, first period, right? So try and be here on time, so you've got the whole time. And if you get extra time, then come early. Okay? So let's say 8:15 start time, maybe. Give you an extra 45. You judge, but kind of figure how much time you might need. So just let me know. We'll talk later. Okay, so an exponential function. So this starts on page 334. It's 6.1, and the definition is given. It's a function of the form Nope. So it's a function of the form y equals a times b to the power of x. Okay, so it's called an exponential function because the variable is the exponent. If you remember order of operations, you have to do the exponent first. So you're going to evaluate b to the x first, and then you'll multiply by a, right? Just order of operations when we do an exponential function. In this case, we have some restrictions. So a can't be 0, because if it is, you just end up with y equals 0, right? And that won't be an exponential function. And b has to be greater than 0. And b can't be 1. Okay, so there's a few restrictions. So a can't be 0, because if it is, the whole thing is 0, so that's just, that would just be a flat line, right? Y equals 0. B has to be greater than 0. It's got to be positive. And b can't be 1, because if b is 1, then 1 to the anything is just 1, and it'll just be a flat line, and that's kind of boring, right? So to look at this, what we're going to do is we'll go into Desmos, right, a little graphing calculator. We'll graph this, and one of the interesting things about Desmos is that I can actually type it in as y equals a bracket b bracket to the power of x, and what it'll allow me to do is add a slider for a and b so that I can change their values, right? So we can look at this, and this is where b equals 1, right? And we said b can't be 1. And we said b has to be greater than 0, so I'm going to go in and change this. And so we'll change that to 0, and 10 is good enough. And maybe what we'll do is we'll, for now, we'll step by. Actually, I'm going to change that to 1. And we will step by 0.5s. Okay. Now, we don't do b as 1, right? So let's just go to b equals 2. So let's take a look at this graph. This is an exponential function. And what I'm going to do is I'm just going to slide the b along, and you can just watch the graph and see how it changes. And we'll come up with some observations as to what's changing and what isn't changing. And what did I do with my notes? I left them back there. So anyways, let's just, here, I'll slide b along, and you can watch b. I'll watch the graph. So what's changing? Now, are there any values of y that are less than 0? Is it going down below here? No. So, you know what? No, I don't want to zoom in. Let's zoom out a bit, just because it's getting pretty big. And let's move this graph down. Because if it's not going to go below the axis, then why should we bother looking there? Okay. So slide along. So this is getting bigger values of b. This is getting smaller values of b. So what's happening? 4. What's not happening? Okay, so let's look at some characteristics, right? Like we did with polynomial function. So how many x-intercepts are there? If we look for x-intercept, is it intercepting the x-axis? Does it look like it?
Wait, what's X? No.
So this, it's not really, right? Okay. So how do you get an x-intercept? What do you set? You set y equal to 0. Okay, if we go back to the equation, which is here, if we go back to the equation, if we set y to 0, and we've got these things, so forget about a, well, let's just say a is 1 for now, okay? So we'll just keep a as 1. Can I ever get b to the power of x? Can I get some number to a power to be equal to 0? No, only if it were 0, right? And we said b has to be greater than 0. So no x-intercept, right? So in describing this, then we will say there is no x-intercept. Let's go look at the y-intercept. So let me just zoom in a bit. We'll have to move this as well. So what's the y-intercept right now? 1. Okay. Now, I'm going to change the b value. What's going to happen to the y-intercept? So watch the y-intercept. What's happening to the y-intercept? Absolutely nothing. It's the answer I wanted to hear. It's going up, it's going down. The y-intercept is here, right? What's happening to the y-intercept as I change the value of b? Stays the same, right? What is it? 1. Okay, so the y-intercept right now is, okay, so the y-intercept is 1. The end behavior. So we talked about end behavior. What's the end behavior? It's going from where to where? Quadrant 2 to quadrant 1. And we're going to add something. I'm going to close this one. Okay, so the end behavior is quadrant 2 to quadrant 1. Sure. Yeah, metal or wood?
Take the wood one. Straighter.
Yeah. Well, I have a straight metal one.
So this is fine.
So the end behavior is quadrant 2 to 1. What's the domain and the range? So what's the domain for this? Are there any x's we can't put in? No. So domain is all real numbers. And what's the range? So domain, set of all x, and the range. So we said there's no x-intercept. So we know that y can't be 0. And it's not going below, so it can't be negative. So then the range is y is greater than 0. Okay, now what do we say? We said b is greater than 0. It's not 1, but when I did this, I put the values from 1 to 10, right? So let's change this. What if it goes from 0 to 1? What's going to happen? Will there be a difference, right? If we go below 1 for a b value. So I'm going to go back here. I'm going to change that to 0. And I'll change this to 1. And we'll make the steps 1/10. Okay, so there's 1. That's no, it's a flat line. So here we go, below 1. Oh, so what changed? And if I make this, change sides. Okay, did the y-intercept change? Did the x-intercept change? Is there now an x-intercept? No. but it's like it changed sides, right, is what you said. That, so we're going to come up with some words to describe this. And we'll say, well, when b is between 0 and 1, did the end behavior change? Is it still quadrant 2 to quadrant 1? Okay. So let's go back here. So this was b is greater than 1. That's the information we had here. This is b is between 0 and 1. Is there still no x-intercept? So that's the same, right? Is the y-intercept still 1?
Yeah.
Okay. Do you want me to go back to it? Or?
No.
No? Okay. Y-intercept still 1. Is the end behavior still quadrant 2 to quadrant 1? Domain still real numbers? Is the range still y is greater than 0?
Yes.
Okay? But something changed and we need to describe that. And the way we're going to describe it is whether the function is increasing or decreasing. So here we'll say the end behavior is quadrant 2 to quadrant 1 and it's increasing. Right? 'Cause remember what it looked like, it was going like this. It was going up to the right. Right? We were going from quadrant 2. We were low in quadrant 2. It's not going to translate well to the video. It's low in, let's do this. It was low in quadrant 2 and then went up. That's increasing. Okay, and it didn't cross. And that was when b was greater than 1. When b is less than 1, it's doing this. So, and by less than 1, remember, it's between 0 and 1, right? It can't be 0 and it can't go negative. So when b is between 0 and 1, this is decreasing. So we're just going to add to our vocabulary from polynomial functions and add to the end behavior to say, okay, it's increasing or it's decreasing, right? It's increasing when b is greater than 1. It's decreasing when b is between 0 and 1. Okay, so there's decreasing. And let me just, let's just go back. So let me just type this in. Y equals a bracket b bracket to the x. And add the sliders in where now I can change them. Okay, so I make this, if I slide this to the right, the b values get bigger and we can see that it's increasing. And that the larger the b value gets, kind of the steeper, right? The greater the rate of increase, right? The greater that it's increasing. And if you think about it, it's because this will become like y equals 10 to the power of x. So when x is 1, we're actually going to get the value of b, right? If a is 1, when x is 1, we're going to get b to the power of 1, which will just be b. So when it's 2, so here's x is 1, right? And if I slide this down, then we can see, look, there's x is, we're around 6 there, right? And now we're around 4. So this is around 4. And now it's around, whoops, and now it flipped. And now it's around 2. Okay, and then we hit 1 where we're not defined, right? That's our flat line. We go below 1, and now it becomes decreasing. Okay, and the smaller that b gets, the greater the rate of decrease, right? That it's going down faster. Okay, so as I make b smaller, so if we go to b is, let's just, from 0.59, change that to like 0.3, 0.3, not 0.3, 0.3. Okay, you can see that that's decreasing faster, right? That it's steeper up here, but it's coming down faster. So as we get closer to 0, we're coming down faster. As we get closer to 1, it's a flatter curve, right? And at 1, it becomes flat. That's no longer an exponential function, so we don't consider the case where b is equal to 1. But just think about, as the b values are really large, it's very steep. As we lower the b values, it comes down. Okay, so b values are large, it's very steep, and it's increasing. As we lower the b values, it starts to come down and get flatter. Okay, when we reach 1, it's no longer an exponential function, and as we go below 1, then it's decreasing. And the more that and if we go negative, you see what happens when there's a negative value for b, there's no graph. So it's not defined when b is negative, right? And that's all what we put in the definition, right? Y equals a times b to the x. Okay, so let's set a b value of 2, and let's play with a. So what's going to happen? So you want to watch this graph, and you want to say, okay, I'm going to start increasing the a values. And what did we say about a? I think we said that a has to be greater than, so a is not equal to 0. For us, I think we're pretty much going to deal with a is always positive. We're not going to do negative a's, but we'll see what happens when a is negative, right? I mean, it's not going to hurt. Either there's no graph or something else is going to happen. So I'm just going to play with the a values. So here, what I'll do is I'll just step over here. And I'll play with the a values over here so you can see what's happening on the graph. Okay, so watch and try and see what's changing, right? So ask yourself, are there x-intercepts now all of a sudden? Or okay, so what's changing? What definitely changed there? A is 2, and what else? The y-intercept is now 2. Okay, A is, let's go to 3. When A is 3, then what? Y-intercept is 3. A is 4. Here, let's zoom out. And let's move this down, because we don't need to see below the axis, right? Okay, so I make A 5, close to 5. When A is 5, what do you get? Y-intercept is 5. A is 6. Oh no, let's just go to 10. When A is 10, what do you got? Y-intercept is 10. So what's A? The y-intercept. What else is a doing to the graph? Let's just take a back to 1. 0 won't work. Okay. So as a increases, what's happening? Gets thinner. Yeah. And the technical term we put with getting thinner is that it's actually being stretched vertically. Right? Everything's being pulled up. And that's what's making it thinner, right? You're grabbing it, you're pulling it up. So it gets thinner. Let's take a back to 1. Okay, so what if a goes below 1? What else we got going on here? Okay, well, the graph didn't disappear and it didn't flip sides, so what's changing? So here, a is a half. What else is a half? Y-intercept, right? Okay. And the graph is getting... It's also being stretched vertically, right? But by a factor of a. But when a is less than 1, then it's getting, more. It's getting flatter instead of thinner, fatter, I guess, right? It's just widening out as opposed to narrowing in. And again, that's part of the vertical stretch. All right, if we take a to 0, then everything just disappears, right? We're just graphing the axis because now we have y equals 0. So that's why a can't be 0. If a goes negative, then what happens to the graph? Okay, it's just like when you have a quadratic and you make the a value negative, it gets reflected. Okay, we're not going to do that, right? So for us, a will always be positive. We can see a can be negative, right? It's not like b, you make b negative and it's gone. Okay, a could be negative, but we're not interested in that. Okay, so a, two things, right? So let's go back here, back here. So the y-intercept is not 1. What is it? A. Okay. Didn't we just do this? Didn't you say 5 times? It's A, it's A, it's A. So the y-intercept is A, right? It's not 1. If A is 1, it's 1. Right? That's where we started, right? Because you don't change both things, right? So if you ever do this, if you want to play with this on your own, by all means, go ahead, decimals.com, right? I mean, there it is. And if you're watching the video, you can play along with it while we're doing it. Don't change 2 things at once, right? Don't slide the A and slide the B, because then it's like, well, what happened? Like, stuff changed, but what's the change? So play with one slider at one time, and you can see what's happening. Okay, so we changed the A value, the y-intercept is A, the end behavior stayed the same, it was still increasing or decreasing based on the B value. Okay, again, let's go back Because I left b at 2, so what if we put b at 0.5? Let's go 0.5. So there's b is 0.5, and I'll play with a again. So a is 5, y-intercept is 5. A is 10, y-intercept is still 10. It's still a decreasing graph. Okay, I don't want to take it down. So it's still a decreasing graph, and A is the y-intercept, and it's also giving us a vertical stretch factor, right? So it's stretching the graph more than it was. Or if A is between 0 and 1, it's stretching the graph less than it was, right? It's making it half of what it was. And then if it goes negative, we don't do that, so don't worry about that. Okay? So that is what's going on with the exponential function. There's one other special. Introducing the letter, ladies and gentlemen, introducing you to the letter E. It's like an episode of Sesame Street. We've been playing with A and B and X, but now it's E. E is actually a special number. It's called Euler's number, or Euler, depending on how you want to pronounce it. But generally, I pronounce it Euler. And I think I have it over here somewhere. If I can get rid of this. Hang on. Here, the number E is a famous irrational number, so you can't reason with it. And it's one of the most important numbers in math. So the first few digits are 2.7, 1828, 1828, 4590, 45, 23536, and it keeps going. And I actually only know the first 20 anyway. So. It's often called Euler's number. E is the base of the natural logarithms, right? And we're getting to natural logs. So we're doing logarithms as the next unit, but we're also introducing the base E. And the reason is it's often found in nature. So if you're doing biological sciences, right, if you're doing nursing or something like that, or any biology and stuff, you're going to run into the number E in an exponential function. Okay? And this is what, this is what y equals e to the x looks like. So I'm just going to go in. Well, we'll just do new graph. New graph, when I type y equals e to the power of x. And you notice it's not asking me, do you want a slider, right? When I put a and b in, it said, hey, do you want to make those sliders? So it knows what e is. Okay, so there's e. Now in this case, a is 1, right? We don't do y equals 2 times e to the x. So a is 1, our y-intercept is 1. When x is 1, we're getting e, which is 2.71828, right? So this is 2.5 right here, and there's 3. So that's the value of e. So e to the x doesn't look much different from y equals b to the x, right? Where b is 2 or 3. It's just somewhere in between there, right? But it is a number that you're going to be exposed to, called Euler's number, used, and it's the limit of natural growth. Okay, like if you worked out, you guys have done compound interest, right? So if we did compound interest, so let's say I gave you 100% interest per year. Here, we'll do this, just a little calculator exercise. Grab your calculator. Let's say I give you 100% interest per year, right? So you know that A is equal to P times 1 plus I to the n. Okay, and we're just going to start with $1, right? Because $1 makes it easy. So we're going to go A is equal to 1. I'm giving you 100% interest, so that'll be 1 plus 1 to the n, which is 2 to the n. So at the end of 1 year, you're going to get $2, right? Okay, what if we compound semi-annually? Then we need to adjust, right? So instead of 1, we go 1 divided by 2 to the power of 2, right? Because now you're getting half the interest, which would be 50% or 1/2, but you get it twice a year. So this is 1.5 squared. So here you would have got $2. Here you get 2 1/4. What if we do it monthly? So now I need a calculator, right? So let's say it's monthly, then it's 1/12 to the power of 12. So somebody work this out. 1 plus 1/12 to the power of 12. I know it's $2 and something. 261. What if you did it daily, right? Daily interest, okay? So what if we do 1 plus 1 over 365 to the power of 365? How much are we going to get, like 10 bucks or 20 bucks now? Because, hey, now we're getting interest 365 times a year. So what does this come to? 2.7, yeah. I'll give you a moment. 2.714?
Yeah.
What if they paid us interest every second, compounded it every second or something? Or what if we got interest 1,000,000 times a year? How much money would we then have? So to do that, we would go 1 plus, well, you'd get 1,000,000th, right? To the power of 1,000,000. And what's that work out to then? So now we're getting interest 1,000,000 times a year. Like, I don't know how many seconds are in a year, but we can figure it out. But 1,000,000 times a year, you're getting interest. Are we going to now get like 10 bucks, 20 bucks, 30 bucks? So go 1 plus 1 divided by 1,000,000. We can hit enter and then go to the power of 1,000,000. Remember, 6 zeros. Everybody got it? 2.718. Keep going. One, 8, 2.
0469.
We could do the same thing. We could do it with a billion. If we do with a billion, then we are going to get a number, and that number is going to be 2.718281828459045. So it's called the limit of natural growth, right? No matter how much we try and grow this interest, we can pay you 1,000,000,000 times a year. You're never getting more than $2.71.8, $2.72 now. Okay. So that's that special number E. All right. Do a couple more things. I'm going to write this. Y equals 3 times 6 to the power x. I don't want you to graph this, but I want your prediction as to the following characteristics, right? So, number of x-intercepts, actually we can move this over a bit. So we'll do number of x-intercepts, make a little turn. The y-intercept, end behavior, increasing, decreasing,
He's like holding vented in the back, old western.
domain, range. So, Sebastian, hat off. Knowing what we know now. Y equals 3 times 6 to the x. How many x-intercepts will there be? What is the y-intercept?
3.
Okay, the y-intercept will be 3. What is the end behavior? Quadrant 2 to quadrant 1. Is it increasing or decreasing? How do you know? It's positive. They're always positive. A and B are always positive, so why is it increasing? What's above 1? Okay, B is greater than 1. That's how you know it's increasing, right? That's your justification, all right? Because the B value is greater than 1. Domain. Belongs to the reals, and the range, y is greater than 0. Okay, so if we were going to sketch this, what would we draw? What would I label this? 3. Okay, so I would label that as 3. Okay, that's our prediction. Quadrant 2 to quadrant 1, y-intercept of 3, etc., etc. Let's go to wherever this is and graph it. Okay, so it's, what was it? 3 bracket 6 bracket to the x. Okay, so we have an increasing function going from quadrant 2 to quadrant 1 with a y-intercept at 3. Right? That's just giving you the coordinate, 0, 3. No x-intercepts, increasing. Okay, let's do y equals, what's my next one? 7 times 1/4 to the x. How many x-intercepts? None. Y-intercept? 7. End behavior? 2 to 1. Increasing or decreasing? Why? Yeah. What we're going to say is b is between 0 and 1, right? Because last one implies, well, it could be 0, it could be negative. Right? B's cannot be negative, and b's cannot be 0. Okay, a can't be 0, you're just being in a flat line. That's the axis. Domain? Range? Both the same, right? Okay. So we have some things that are constant here, right? And we have some things that change. So what changes? Okay, and what's constant? This is constant. So things that change are the y-intercept, which is related to what variable? Which variable does the y-intercept? A. And the value of b tells us whether the function is increasing or decreasing. How does that work? Okay, that's our prediction. Let's try it. So I'm going to go 1/4 and change that to a 7. Okay, so the y-intercept probably is 7. Let's find out. Oh, here it is, labeled for us nicely, right? 0, 7. We have a decreasing function, right, going from quadrant 2 to quadrant 1 with a domain x belongs to the real numbers and a range y is greater than 0, which is every single exponential function, right? So there's that common stuff, right? They will always go quadrant 2 to quadrant 1. The domain is always x belongs to the reals. The range is always y is greater than 0. What changes is whether it's increasing or decreasing based on the value of b. And what changes is the y-intercept, which is based on the value of a. Now all of this is in the key ideas on page 346. So page 346, and that's 6.2. Look at that. See, we've done like 2 sections in how long? Not that long, right? Yesterday was like 1 section in like a whole period. And that's just the way it goes. So there's key ideas on 336 and 346. Okay, we're done 6.1 and 6.2. They do some stuff with tables of values, and you can do stuff with tables of values here because you can hit edit and say give me a table, and it'll give you a little table of values, right? And you can see what's happening for that particular graph, right? So there's 7. So you can see that when we get -2 for x, we're getting pretty big numbers here, you know, 112 and 28 and 7. And now we start to get into the smaller numbers. And the larger the x values go, the smaller the y value. The larger the x values get in a negative direction, much larger this gets. Okay? And if I change this, let's go back to the other one, which was the other one? 3 times 6 to the x. So So 3 and 6. Okay, and remember the y-intercept occurs when x is 0, right? So you look down where x is 0 there, and there's your y-intercept of 3. And you can see that as the x values are getting larger, 1, 2, then the y value is getting much larger. It's an increasing function, and same thing, going smaller. And here, it's showing you the points, so you can ask, just, give me the coordinates of these points, because they match, they match up with what's in the table there. Well, I can't make them stay. And you can trace along this too, right? So I can trace this, and it will show me, it'll show me the points. If we want to see it get bigger, we can just zoom out, zoom out, zoom out. And we can see it get bigger. And again, you can, trace, give me a point. No, give me a point. Okay, and then I can trace along the graph, okay, and see the values. Not well, you can do it a little better with a mouse than with a finger on it.